to Chapter 6 of S. Hawkman's book, A Brief History of Time, Stuff and Things. From the Big Bang to Black Holes. Chapter 6 of his book, S. Hawkman. And it's Series 1, Episode 4, me reading out S. Hawkman's book. So here we go. The picture that we now have from Oppenheimer's work is as follows. The gravitational field of the star changes with the paths of light rays in space-time from what they would have been had the star not been present. The light cones, which indicate the paths, followed in space and time by flashes of light emitted from their tips, are bent slightly inward, near the surface of the star. This can be seen in the bending of light from distant stars observed during an eclipse of the sun. As the stars contract, the gravitational field at its surface gets stronger and the light cones get bent inward more. This makes it more difficult for light from the star to escape, and the light appears dimmer and redder to an observer at a distance. Eventually, when the star has shrunk to a certain critical radius, the gravitational field of the surface becomes so strong that the light cones are bent inwards, so much that light can no longer escape. Figure 6.1. Showed you this last time, but told you about it. Singularity. It didn't say what I thought it did. Light ray emitted at the time the event horizon forms. This is time. Look at it. Time. Time. Think about it. Time. Interior of star. It's just there. Spot there. Just look. Diagram 6.1. Okay. According to the theory of relativity, nothing can travel faster than light. Thus, if light cannot escape, neither can anything else. Everything is dragged back by the gravitational field. So one has a set of events, a region of time, a region of space-time, from which it is not possible to escape a region. From which it is not possible to escape to reach a distant observer. This region is what we now call a black hole. Its boundary is called the event horizon, and it coincides with the paths of light rays which just fail to escape from the black hole. In order to understand what you would see if you were watching a star collapse to form a black hole, one has to wonder, or even remember, as it actually says, that in the theory of relativity there is no absolute time. Each observer has his own measure of time. The time for someone on a star will be different from that for someone at a distance because of the gravitational field of the star. Suppose an intrepid astronaut on the surface of a collapsing star, collapsing inward with it, sent a signal every second, according to his watch, to his spaceship orbiting the star. At some time on his watch, say 11 o'clock, doesn't say AM, the star would shrink below the critical status, radius at which the gravitational field becomes so strong nothing can escape, and his signals would no longer reach the spaceship. As 11 o'clock approached, his companions watching from the spaceship would find the intervals between successive signals from the astronaut getting longer and longer, but this effect would be very small before 10:59. they would have to wait only very slightly more than a second between the astronauts' 10:59:58 signal and the one he sent when his watch read 10:59:59. But they would have to wait forever for the 11 signal. The light waves emitted from the surface of the star between 10:59:59 and 1100 by the astronaut's watch would be spread out over an infinite period of time, as seen from the spaceship. The time interval between the arrival of successive waves of the spaceship would get longer and longer, so the light from the star would appear redder and redder and fainter and fainter. Eventually, the star would be so dim that it could no longer be seen from the spaceship. All that would be left would be a black hole in space. The star would, however, continue to exert the same gravitational force on the spaceship, which would continue to orbit the black hole. Doesn't mention it. It's the Drost effect. Drost. D-R-O-S-T-E effect. Yeah. Stuff S-Hawk Man. This book marries child's wonder to a genius's intellect, and journey into Hawkman's universe while marvelling at his mind. Sunday Times. Intro by Carl Sagan. I've said that before. A few other little things that I've got to say. 1988. It's an up-to-date book. Hawkman's words used. Master of the universe. One scientist courageous voyage to the frontiers of cosmos. Newsweek. He can explain the complexities of cosmological physics with an engaging combination of clarity and wit. He is afraid of extraordinary power. Observer. To follow such a fine line that exposes such great problems is an exciting experience. Sunday Times. We couldn't even understand this book. What's he even on about? The sun. Look at it. It's cool.